All right. Good morning or good afternoon, class, whatever time it is when you're watching this video. We are looking at our day 4 material for Math 208. So going over our schedule, let me share my screen here. So for the day 4 material, we are looking at sections 2.3 and 2.4 of our textbook as we continue into chapter 2. Where we've started our discussion into graphical methods for types of data, whether it be quantitative, so it's numerical in nature, or if it's qualitative, meaning it's non-numerical, it can fit into a category, but it doesn't have a number associated with the data which is collected. However, as we continue, we really want to look at statistical numerical methodology for studying a sample set of data. And so we're going to start our study into numerical analysis today as we're going to look at how do we determine what we would consider to be the center or essential tendency of data, as well as variability. Is the data spread apart? Is the data kind of ranging over a lot of numbers? Or are we talking about data which is very close together, which has less variability if a lot of the numbers are the same kind of numbers? All right. We'll talk about how to take those kind of numerical calculations in today's video. Okay, so again, this is day 4. We'll go ahead and start in section 2.3 for this video, where we'd like to look at how do we determine central tendency. Now, we've already seen this kind of graph shape earlier, or in the day 3 video. So let me go ahead and switch to the whiteboard behind me. So let me turn off the screen share. Okay, so if you look at the board back here, we already saw from last class when we create histograms for numerical data, oftentimes we're going to see this kind of shape where when we're graphing the frequency of different data entries, then oftentimes we may have a histogram that kind of has this like hill shape or mound shape that looks something like this, where if I were to draw a curve over this, it would look something like this, all right? So the height is referencing the frequency, and so if something has a lower height or is smaller, then that entry is less frequent. Some common examples of populations of data that look like this, you can think about like average height. Most people have a height that is somewhere here in the middle, where a majority of the population is going to have a height around the average or around some kind of middle. You're going to have some people who are on the shorter side. There's fewer of those people who are extremely short. You're also going to have some people who are extremely tall. And so there's going to be fewer people on that side, but they can be larger or smaller than whatever this kind of middle is. And so when we're dealing with population data that has this kind of hill shape, one thing we want to determine is, well, where is this center? How do I determine what actually is this most frequent, most common data entry where I have this clustering around this middle where there is a higher frequency here in the middle. And so it's a central tendency for this kind of population. All right. Oh, hold on. The cat got trapped in here again. Okay. So this is our goal. We want to figure out how do we find this middle. And there's a few different ways of doing this. One option would be, well, if it is, in fact, the most frequent data entry, then that is, you may recall from high school classes or other kinds of math classes that you've had in the past, to find the most frequent data entry, that is called the mode. And so that would be one option. So we could find the mode for a set of data is the most frequent data entry, whatever that may be. All right. Oh, that purple. I need to get a new marker. This marker is starting to dry out. Let's see. I don't know if I have another marker in here right now. Might need to get another marker from my office when I go back to campus. So I apologize, that might be hard to read. You can also see the definition for the mode in the textbook. So the mode for a set of data is the most frequent data entry. Okay, so I apologize, this is probably very terrible to read. I need to get a new marker, so apologies for that. But again, this definition is also in the textbook. So the mode, it's whatever's got this highest frequency, okay? Now, it is possible for some sample set of data, you could have more than one mode. Consider a sample, which looks something like, I could have 1, 2, 2, 3, 3, and 4, right? In which case, well, 2 has a frequency of 2, 3 has a frequency of 2. They both have the same highest frequency. And so in this case, I would actually have two modes where 2 and 3 are both the mode for this sample set of data. All right. So a mode, you can't have more than one of it, and that's okay, that's fine. You would just list both if it's a homework question, or if it's a test question, you want to list both then if there are multiple data points which have the same highest frequency. All right, so mode is one option. Another option would be to calculate the average. So the average, you've probably seen this formula before. This is also how averaging for a homework assignment or averaging for a test assignment is calculated. If you want to determine what is the average test grade, you take all of the test grades, you add them all together, and the thinking is, well, if I add all of the data points together, and then I divide it out equally between the number of data points, in other words, the sample size, then that would be if I equalize all the points, what would that middle be, right? And so for this sample, it has a sample size of 1, 2, 3, 4, 5, 6. It has a sample size of 6. And so if I want to calculate the average here, or in other words, what is called the mean, then I would add up all the points and divide by the number of numbers, the sample size. So I'd have 1 plus 2 plus 2 plus 3 plus 3 plus 4, all divided by 6. And we would get an average, or the mean, of, well, if I add it all up, 1 plus 2 is 3, plus 2 is 5, plus 3 is 8, plus 3 is 11, plus 4 is 15. We would have 15 divided by 6. And for a test or a homework, it's okay to leave your answer as a fraction. I would give that full credit. It would be okay to leave it like that. But if you want to write it as a decimal, oh, my calculator's in the other room. Bear with me one moment. Okay. So we go to the calculator, 15 divided by 6, we get an answer of 2.5. And if we come back up to the sample, does that make sense? Well, sure. 2.5 is actually right here, dead in the middle. Half of the data is to the left, half of the data is to the right. All right, so the average here, in this case, is a great way of trying to find this central tendency where I have a lot of data which is close to 2.5. I have the two twos, which is pretty close, and I have the two threes that are pretty close. Okay. Now, another way to try to estimate this central tendency is to calculate a median. What is the median? Well, the average can actually be messed around with depending on the data. We'll look at this a little bit later in this video. Um, but the median is always what is the exact middle of the data, where half is to the left, half is to the right. In order to calculate a median, you want to first list all of your data in order from least to greatest. And so in the case of this sample I just made up, if I want to find the middle, well then I'm quite literally just going to cross out points until I get to the middle. So I've crossed out 2 from the top, 2 from the bottom, but now as I'm trying to find the middle, because I have an even number of data points, my middle is exactly between 2 and 3. So then lo and behold, what should the median be? If the median is supposed to be exactly between 2 and 3, well, you can already guess, then that should be 2.5. But in terms of a calculation to find the exact middle between two numbers, that's the same thing as averaging those two numbers. So 2 plus 3 is 5, divided by 2, and we get a median of 2.5. Okay, so this gives us 3 ways of trying to determine a central tendency. I could look for a mode, all right? The mode in this case was 2 and 3. I had 2 different modes at the same time. The average was 2.5, which told me more exactly an actual middle, and the median also gave me 2.5. So the median is oftentimes our most reliable way to get an exact middle, because whatever it is, half of the data is always to the left, half of the data is always to the right of it. So it's always in the exact middle. In this case, for this example, the mean and the average, or the median and the average, turned out to be the same number. That's not always going to happen. That's just how it worked out for this example. And we'll see other examples in a moment where this doesn't always work out. But in this case, it did happen to be the same number. All right. You'll also see from this, the average and the median do not have to be a number which is actually present in the sample. They're just a number that's trying to indicate, well, what is my data close to in the middle? Where do I have this central tendency that a lot of my data tends to gather around? That's what these calculations are trying to tell us. They're not actually telling us an exact data entry, which is equal to that number. Because in this case, there is no data entry in the sample, which is 2.5, right? It's just giving us an approximation for what my data is close to in the middle. Okay? So let's look at a different example where the mean and the average could be very different from each other. In this case, they're the same, but again, that's not always going to happen. All right. So in a previous video, we were talking about a made-up sample where we're looking at ages for a classroom. So I could have a class where maybe I have an 18-year-old, a 20-year-old, a 21-year-old, maybe there's another 18-year-old, and maybe in this particular class, there's like some middle school genius who's taken the class, and maybe there's a 12-year-old. Or, you know what, let's say 11. Make it more extreme. We have an 11-year-old. Okay. Now, what's going to happen here as we try to calculate the mean, the mode, the median, what's going to happen? Well, first, okay, the mode is probably the easiest to see. 18 has a frequency of 2. The rest of my data entries only have a frequency of 1. So 18 is the mode here that is the most frequent data entry. But now if I try to find a median, I have to first organize from least to greatest. So I have 11, 18, 18, 20, and 21. Okay. Now to try to find my median, I need to find what's in the exact middle. So I'll just make these little dots just to indicate what points I've marked off. One from the top and bottom, a second one from the top and bottom. And so my median is right here in the dead middle at 18. Half of the data is to the left of 18, and half of the data is to the right of 18. All right. So this gives me an exact middle for my sample. But what happens is I try to calculate an average now. In this case, because I have this 11 in here, that 11 is, as you might guess, is kind of an outlier for this sample, and it's actually going to pull my average away from the middle. So if you try to calculate this average, I'm going to add up all the numbers, 11 plus 18 plus 18 plus 20 plus 21, and we're going to divide by, it has a sample size of 5. And so it has a mean of, we go to a calculator, we will get here 11 plus 18 plus 18 plus 20 plus 21 divided by 5. And we have an average of 17.6. So, all right, in this case, because a lot of my data is closer to 18, 11 is not pulling the average that much away. Maybe this is a bad example. But if I had a more extreme number, and let's just play with this for a moment and see what happens. What if I had maybe, let's say, an 8-year-old in the class, even more extreme. Now, all that 8 change, which is not changing the median, but what does it do to my average now? I have this 8 instead of an 11 there. So I have 8 plus 18 plus 18 plus 20 plus 21. I got 85 divided by 5. And now in the case of this example, and it's not that different because after all, 4 out of 5 of this sample are pretty close to 18, right? A lot of these numbers are closer to 18. So what are we getting at here? As we just saw, when we have data points which are farther away from whatever this middle is, that can impact the mean and pull the mean away from the middle. And so when this happens, the mean can be shifted, and then sometimes the mean is not always a good tendency, especially when we have outliers. Now, later in chapter 2, we'll talk more about specifically how do we determine if a number is actually an outlier or not. We're not going to worry about that for today, but for right now, we just want to highlight that this can happen where it might pull the mean away from the middle, in which case the mean would not be a good indicator of a central tendency, right? This also does a good job of showing when data can be called what we consider to be skewed. If I create a frequency distribution for this sample that we have here, I have one data entry, 8. So that would have a frequency of 1. And then way over here to the right, I have 18 with a frequency of 2, 20 with a frequency of 1, and 21 also with a frequency of 1. Now, first of all, this distribution that we've just created, this frequency table, or frequency graph, I should say, for this sample, doesn't really look like that hill shape we were talking about a moment ago, right? The mode and the median are both occurring kind of here in this middle where we have this highest frequency. but my average in this case has been pulled to the left. So I have my mean and then my median. Okay. When this happens, we consider the data to be skewed because there's some kind of outlier which is pulling the average away from the middle. So when we have what is called leftward skewed or leftward skewness, which is what is happening here in this example, this means that the average is less than the median. So in terms of skewness, we're always trying to determine what is the relationship between the mean and the median. If the mean is to the left of the median, then it's leftward skewness, right? Because the median is always the middle. If the mean is to the left, then we call that leftward skewness. If the mean is to the right, then we call that rightward skewness. All right. And all skewness is indicating is the average actually in the middle or not? If it's not, then which direction is the mean being pulled away from the middle? All right. So that's what skewness is going to mean for us as we're trying to make these calculations for central tendency. All right. So let me now return to the textbook. So I'll share my screen again. So here we go. All right, we've been talking about central tendency for a set of data, and we were looking at when data sort of has this hill shape, right? Then the center is wherever this highest frequency is occurring. Another thing we could try to determine about a set of data is the spread, or in other words, the variability. How spread out is my data? Is my data all close together, or do I have numbers that are far apart? That could be another numerical characteristic that we're trying to determine about a sample set of data. Now we'll talk about how to determine spread, or what is called variability, in section 2.4. We'll do that in a moment. But we want to get through 2.3 here, all right? So our definition for the average, which we talked about earlier with our examples, the formula for the average, we saw that on the board. And they do this example here. This is with a different set of data where we have 5, 3, 8, 5, 6. And you can see here from this textbook example how they make this calculation, okay? Some other examples here. Now, we also want to highlight notation as we move forward, as notation is going to be important as we look at more complex statistical questions. So first, when we're talking about an average, we have to make the distinction of if we're trying to study a population set of data, sometimes we have the entire population, right? If I'm looking at the population of a classroom, I could collect all of that information, right? But if I'm trying to say, look at the population of everyone who lives in North Carolina, well, that's going to be hard to collect, right? I'm not going to be able to very easily collect information on every single person that lives in North Carolina. That's going to be a lot of work. It's going to take a lot of time. That's going to be difficult. So when we're trying to study a larger population, what we take then is a sample, and our hope, as we talked about from chapter 1, is that if it's a good sample, then the average from our sample should be close or approximately the same as the population average, all right? But there's no guarantee of that, right? And so we want to make the distinction here with the notation. A sample average and a population average could be different numbers. Despite our best efforts, they might be different. So when we're talking about a sample average, we're going to use this symbol that's called X bar, where we have X and then there's a horizontal bar above it. And when we're talking about the population average, we'll use the Greek letter mu. Now this kind of looks like a cursive U, but it has an extra tail on the front. That's the symbol we're going to use for a population average, all right? So both of these symbols are going to be used as we continue in the course, but we want to make the distinction. Am I talking about a mean from the sample, or am I talking about a mean for the entire population? All right. So we have these two different symbols. Now we have our definition for the median, which again, we saw examples of this on the board a moment ago. And when it comes to the mean, or the median, we're also going to use different symbols. For a sample median, I'll use the letter M. For a population median, we have the Greek letter eta. It kind of looks like a cursive N. Although, to be honest, the population median, we're not actually going to use that much in this class, so don't worry about that symbol as much. Um, but keeping track of the sample mean and a population mean are going to be more crucial as we continue in the course, right? So they give an example of finding a median. We did that on the board. Now, when we have skewness, this is when the mean and median are far apart. Again, saw this on the board. Rightward skewness means the mean is to the right of the median. The mean has been pulled to the right. Um, when the data is not skewed, we have what is called perfect symmetry, right? If the median and mean are directly at the same position, then that means I have half of the data to the left, half of the data to the right, and I have this symmetric picture where this hill shape is being nicely divided in half. This idea of symmetry is going to be crucial as we continue studying these types of samples. But for today, we're just trying to introduce some of these concepts. All right. Leftward skewness, that means the average is to the left of the median. It is less than the median. And the mode, this is whatever data point just has the highest frequency. And again, you could have more than one mode at the same time. All right. So this will wrap up section 2.3 for us. We can now look at 2.4 for the rest of this video, where we have an idea of how to calculate a central tendency. But now, how do I determine variability? How spread out is my data? And on one hand, we could just calculate what is called the range, which you've probably seen in a past high school class, where a range is calculated by quite literally, you take the maximum number and you take the minimum number and you subtract the difference. That is one way of determining, well, how much is my data spread out? How much range do I have in my data? But the range is not always a great indicator of variability, because after all, we're trying to figure out, well, how much does my data actually vary? Is my data very close together, or is it more spread out? Look at these two different pictures here on the graph. I have data which is ranging from 0 to 5 for both of these pictures, right? For both of these graphs. They have the same range. Both graphs have a range of 5, okay? But in terms of variability, well, look at the height differences here. For this second graph, I have this higher frequency in the middle, and there is less data that is farther away. Most of the data stays in the middle, and there's less data which is more spread out. And so in this regard, this graph with this kind of peak in the middle has less spread, less variability, as more of the data is clustered in the middle. But the first picture, it has the same average, the same median, the same mode, and yet the peak is not as extreme in the middle. I have more data entries with a relative frequency that are more spread out. There is more data which is farther away from the middle. And so in this regard, when we're trying to calculate variability, this first graph has higher variability because there are more data points spread out from the middle. Versus the second graph, there are less data points that are spread out from the middle as I have this more extreme peak in the middle. So how do we actually calculate this variability? So we have sample 1 and sample 2 here making a comparison, and I'm going to switch to the whiteboard here. So let me turn off the screen share. All right. And for this example, we have two different samples which have the exact same average. They have the exact same median, but they have different spread, different variabilities. All right. So for sample 1 here, and I'll use S subscript 1 to indicate I'm talking about sample 1. So I'll use a subscript here. I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And they calculate the average here to be 3. This is a sample average, so I'll use the symbol X bar. Okay. Sample 2, on the other hand, has data entries 2, 3, 3, 3, 4. All right, and the average here is also 3. So they have the same average. They have the same central tendency. But we'll see here there is a difference in terms of their variability. How am I determining spread in this case? Like we were talking about a moment ago, what I'm trying to determine is the distance from this middle. Do I have a lot of data which is close to the middle, or do I have a lot of data which is far away from the middle? And so when I'm calculating variability, I'm taking each data point and I'm looking to see how far away from the middle is it. Well, the data point 1, if I subtract here, 1 minus 3, that has a distance of, well, it's -2 away from the middle. 2 minus 3 has a distance of -1 from the middle. 3 minus 3, well, that's a distance of 0. 4 minus 3 has a distance of 1. And 5 minus 3 has a distance of 2. All right. Now, when we're talking about distance, whether it's negative or positive, that's not really that different. Imagine, if I'm looking at a map, if I go 2 miles north of my house, well, then I'm 2 miles away. Or if I go 2 miles south of my house, I'm still 2 miles from my house. Sure, it might be a different direction, but it's just a distance, right? The negative doesn't really matter here. I'm just trying to determine how far away from my central tendency am I? How spread out is my data? Okay. But take a look at the second sample. Now when I calculate variability, 2 minus 3 is -1. 3 minus 3 is 0. 3 minus 3 is 0. 3 minus 3 is 0. And 4 minus 3 is 1. Well, now as I'm looking at how much does my data vary from the central tendency, well, it doesn't vary that much. I only have 2 data points which are different from the middle, versus here I have data points, or I have more data points, which are farther away from the middle. So in this regard, sample 2 we would consider to have lower variability. Sample 1 would have higher variability. They have the same central tendencies, but different variabilities. Okay? So we would like a formula here. How do we actually calculate this variance? So I'll go ahead and put the formula here. This is the same formula which is on page 66 of our textbook. So sample variance, which will be written as S squared. This is S raised to the second power, S squared. This will be calculated as the sum. So we have the Greek letter capital sigma. You can also see it in the textbook, where I am going to sum over all of my data points, where if I have a sample size of n, this is an iterator notation. So when I equals 1, I'm going to start with the first data entry, x subscript I. So x sub 1 will be the first data entry. X sub 2 will be the second data entry, so on and so forth. And for variability, we're concerned with, well, what is the distance from the average? Is it close to the average, or is it far away from the average? Now, when we're talking about distance, like I said a moment ago, the positive or negative distance doesn't really matter, right? In fact, -2 I want to consider to be a positive distance because that is still, whether it's positive or negative, that would still be like 2 miles away from my house. So to get rid of that negative, in our formula, we're going to raise this to the second power, all right? So we're going to raise it to the second power since when we square something, a negative squared will become positive, all right? But I'm trying to get an overall big picture of what is happening with this variability. In other words, I want to average the variability. On average, how far away are my data points from the middle? And so after we sum up all of these distances, all of the different variabilities, then I'm going to divide, and my marker is about to die, but I'm going to divide by n minus 1. Okay? And we're doing this to kind of average. Now, why is it n minus 1 instead of n? This is just because since the average is already being treated as like this point kind of in the middle, where we're subtracting all these points from, instead of dividing by n, we're going to divide by n minus 1. So we're not like double counting that average in the middle. Okay? So there is this formula. It's the same formula in the textbook. Now I'm going to erase this formula, so go ahead and write it down or pause the video. And we're going to use it to calculate the variance for these two different samples. Okay. Now, lucky for us, in this calculation, we already have the distance, where each x, how far away from the average is it? Next is to square the distances and add it up. So for sample 1, I'm going to have -2 squared plus -1 squared plus 0 squared plus 1 squared plus 2 squared. And we want to divide this by 1, 2, 3, 4. We want to divide it by 4. We're going to divide by n minus 1. If my sample size is 5, then we divide by 4. All right? So then for this first sample, my variance, which is s squared, equals, we go to a calculator. This is going to be 4 plus 1 plus 1, plus 1 plus 4, right? 4 plus 1 plus 0 plus 1 plus 4. I'm going to divide by 4. And we have a variance of 2.5. This is giving us an average of like, well, how far away are my data points? Now this is a squared distance, right? These distances weren't originally squared, so this number is a little bit bigger. But that's okay. We'll just leave it like this for now. In the case of the second example, how do I calculate its variance? Well, I'm going to take the distances, I'm going to square them and add them together. -1 squared would be 1. Plus 1 squared is also 1. Again, divided by 4. And now, my variance for the second sample is 2 divided by 4, or in other words, 0.5. So we see here the extreme contrast. Sample 1 has a variance of 2.5 that has this greater spread, this greater variability, versus sample 2 has a variance of 0.5. Most of the data is pretty darn close to the middle, all right? And so it has a smaller variance. So this gives us a way to calculate this variability directly, and we can see for two different samples, while they might have the same central tendency, the variabilities could be widely different from one another. Okay? So we have those calculations from the textbook. But this is, after all, a squared distance. If I'm just trying to find these regular distances without squaring them, then we need a standard deviation. So standard deviation, we'll use the letter S. You find the standard deviation by, well, once you have the square root, or sorry, not square root, once you have the variance, which is S squared, I want to get rid of that square. And so we will take the square root of S squared. In other words, we take the square root of the variance to find the standard deviation. So that would be the square root of 2.5. The standard deviation for the first sample then, if we go to a calculator, we're going to have 2.5. We want to take the square root of that. And we're going to have a standard deviation of 1.58. Which now, this makes more sense. This is saying, on average, my data points are about 1.58 away from the center. Which, yeah, that's mostly true. Some of it is 2 away, some of it is 1 away. One of them was 0 away, but on average, 1.58-ish. That's what standard deviation is. This is how we calculate standard deviation. This is going to be super, super crucial from like here to the end of the semester. We're going to have lots of calculations and different formulas which rely on standard deviation, but we first have to understand how do we calculate standard deviation. Look at the second sample. Once you have your variance, take the square root of it. So the standard deviation is the square root of 0.5. And it has a standard deviation then of, go to a calculator, square root of 0.5, and we get 0.71. 0.71. So on average, we have data points which are 0.71 away. Now this doesn't exactly make as much sense, but we see like, well, there are these points that are almost 1 or fully 1 away, and all these points in the middle, but it still has a much smaller variability, a much smaller standard deviation compared to the first sample. Okay? So this is how we will directly calculate variability for any sample we look at for any type of question. All right? So let me turn off the screen share and we'll go back to the textbook. Or no, I need to turn on the screen share. Back to the textbook. Here we go. Okay. So we have our formula for variance, which is s squared. And then if we want to find standard deviation, we take the square root of the variance. Okay? Now, again, we want to be careful with notation. When we're talking about a sample variance or a sample standard deviation, we're going to use the letter S. If we're talking about a population variance or a population standard deviation, we're going to use the Greek letter sigma, lowercase sigma. Now, this kind of looks like a cursive O with like a little tail sticking off the side or sticking off the top. But again, we want to make the distinction here as these calculations might be different between the sample and the population. We hope they're the same if we have a good sample, but if we have a bad sample, they might not actually be that close. All right. Now this example, they show the calculation for the standard deviation for sample 2, which we just did on the board, okay? Now they break it down more step by step, but you can see it's the same thing as what we just did a moment ago, all right? And that will conclude section 2.4 for today, all right? We'll continue in chapter 2, on day 5, and then we have 2 more lectures to finish chapter 2, and then we will be ready for test 1, okay? So test 1 is going to include all the chapter 1 material, this chapter 2 material. There will be review questions that I will post to Canvas with their correct answers, so you can use that as a study guide, study material for the test. And if you understand those review questions, you're going to understand pretty much everything on test 1 and be prepared for that, all right? Now, I will send out an announcement with more information on how the test is going to go. So don't worry about that just yet, but just be mindful that it is coming up in in the next few days. All right. So last thing for today, let's look at our participation question, where we are asked to find the standard deviation for the sample 2, 3, 3, 3, 4. But don't have to calculate it again since we did it during the video. So our answer here for today, the standard deviation, lowercase s, is equal to 0.71. So you can type that in, hit enter, and you will have your answer for participation day 4. All right. As always, if you have questions, feel free to email me, come by office hours. Otherwise, best of luck, and I hope you have a great day. All right. I will see you in the next video.